We know Agentic AI has the potential to rapidly accelerate hardware and software co-design. But when you try to move past isolated, small-scale problems, the orchestration layer will fracture under the load. Writing bespoke scripts to pipe LLM outputs into CAD tools works on a single local machine. Scale that logic across hundreds of heterogeneous servers, and the scripts snap under the weight of dependency conflicts, node failures, and strict resource requirements. Giving an AI agent unfettered access to a system-on-chip framework isn't the solution either. Hardware design demands absolute determinism. An unconstrained agent will inevitably hallucinate or skip steps, failing the rigorous verification standards required to tape out a functional chip. Researchers at UC Berkeley developed CHIA, co-designing hardware and software with intelligent agents, to address the specific orchestration bottleneck. CHIA treats the hardware workflow itself as a programmable, distributed graph rather than a linear, brittle script. Realizing the promise of AI-generated hardware depends on a resilient execution environment that can manage the immense scale of hardware validation. System-on-chip workflows require a highly heterogeneous set of computing resources. Compiling RTL might happen on local CPUs, while bitstream generation needs FPGAs, and simulating trillions of instructions requires massive clusters of cloud instances. This is the foundation of the CHIA architecture. It pools local physical machines and remote cloud servers into a single unified cluster. On top of these physical machines, CHIA specifies a set of logical workers. These virtualize the environment, ensuring each task has exactly the software and hardware it needs to execute. Nodes in the loop request specific resource tokens, like Verilator or Claude creds, and the runtime dynamically schedules them to the appropriate logical worker. These logical workers rely on strict containerization to isolate non-deterministic LLMs from sensitive proprietary CAD tools and PDKs. This ensures an agent can't access privileged information or corrupt the environment. This separation of the substrate allows researchers to instantly scale hypercloud experiments without manually managing machine-specific dependencies. The behavioral logic of the workflow sits above the hardware in the CHIA loop. The loop is composed of nodes, which are modular Python functions representing discrete tasks, like calling an LLM API, building chisel code, or running a Verilator simulation. These nodes are connected by edges to form a directed cyclic graph, orchestrating the entire design flow. A programmatic edge defines the human-controlled logic. It enforces a strict flow, such as automatically routing data back to a starting node if a verification test fails. An agentic edge, however, delegates bounded decision-making to the LLM. Using the Model Context Protocol, the agent decides when to read or write files, and how to adapt its reasoning based on the results of previous nodes. Balancing programmatic enforcement with agentic flexibility allows engineers to harness LLM creativity while strictly maintaining deterministic hardware verification standards. At this scale, failures are inevitable. Simulators crash, servers go offline, and LLMs occasionally generate malformed payloads. CHIA utilizes Ray as its distributed backend, enabling fully asynchronous execution across the cluster. The framework instantly detects a crash and reschedules the failed node's task to another logical worker with the requested resources. The runtime also handles sub-process tracking to kill zombie CAD tasks, alongside caching and node bypassing. These features prevent resource leaks and allow long-running loops to recover from interruptions without repeating days of work. Without these integrated resilience features, iterative multi-day hardware workflows would be mathematically certain to fail from isolated hardware dropouts. To validate the framework, the team used CHIA to force a Gem5 microarchitectural simulator to align perfectly with a Boom RTL implementation. Keeping simulators up to date is a massive engineering bottleneck. As the hardware RTL changes, software models drift, requiring hundreds of human engineer hours to restore accuracy. This CHIA loop was designed to solve that problem autonomously. On the left, explicit orchestration compares Gem5 cycle counts against the ground truth Verilator results and persists that data to a database. On the right, Agentic orchestration gives Claude Code the bash and build tools needed to actively rewrite the Gem5 core models based on those comparisons. Isolating the agent's code generation within this rigid verification loop allows for iterative design without risking the corruption of the simulator's logic. This autonomous alignment process ran for 10.5 days, spanning 200 distributed iterations across the CHIA cluster. This heat map tracks the cycle count difference across 36 benchmarks. Over time, the deep red of misalignment shifts to pale blue as the agent converges on the correct microarchitectural parameters. Around entry 110, the process hit a plateau. The agent's iterations were no longer yielding significant alignment improvements. Researchers leveraged CHIA's modularity to code a new run and compare tool in 1 hour and hot-swapped it directly into the live loop. The agent immediately utilized the tool to test its own hypotheses, smashing through the plateau and driving the final error rate down to 2.8%. This proves that CHIA's ultimate advantage is agility, the ability to inject new analytical tools into an agent's reasoning loop on the fly. The Gem5 alignment loop is only one specific configuration of the CHIA abstraction. The same framework has orchestrated everything from RISC-V ISA extensions to evolutionary architectural discovery and automated critical path optimization. LLMs can now generate functional hardware code with relative ease, but verifying and scaling that code depends on a resilient validation pipeline that survives the rigors of distributed execution. By open sourcing the distributed orchestration layer, CHIA allows researchers to stop fighting brittle scripts and focus their attention on discovering the hardware architectures of the future.